Let's continue with our exploration of the thermal properties of materials and discuss thermal expansion. You may remember that we have already alluded to the fact that materials change volume as a function of temperature when we briefly discussed how a glass thermometer works. Essentially, when liquids and solids are heated, they expand because of the increased motion of their atoms or molecules. The atoms vibrate and move faster, so the bonds between the atoms are stretched. This increases the average distance between the atoms, and hence the materials are seen to expand. This is an important phenomenon to take account for engineers designing large objects. For instance, a long bridge will slightly increase in length on a hot day compared to a colder day. As such, bridges are designed with thermal expansion joints, which enable them to change length without causing the bridge to buckle. This is also an issue for railway tracks, which is why tracks were traditionally made with spacers, which caused the iconic railway clickety-clack sound of train travel. So let's look at this concept in more depth and put some equations and numbers on these changes. Thermal expansion, linear. Let's take a metal bar and think about what happens when we change its temperature. What will the change in length, delta L, be proportional to? We would expect a greater change if we had a greater change in temperature. So we can say that delta L would also be proportional to the change in temperature, delta T. Well, if we took a longer bar, we would expect a greater change. So we can say that delta L will be proportional to L naught, the initial length. So now we have that delta L is proportional to the original length, L naught, and the change in temperature, delta T. Now, in a similar way to how we generalize the equation for specific heat, we can now add a material-specific proportionality constant. In this case, it's called alpha. Alpha, written with the Greek symbol alpha, is called the coefficient of linear expansion. As an equation, we now have delta L equals alpha L naught delta T. Can you work out the units of alpha? You might want to pause the video and give it a go. So we can see if we rearrange the equation above that alpha would equal the change in length L, delta L, divided by the length, divided by the temperature. So the units are simply per Kelvin, or Kelvin to -1, as the units of lengths are cancelled out. It may be easier to think of this in terms of fractional or percentage change in length. So we can rearrange the equation to show that delta L over L naught equals alpha delta T. This helps us understand that each bond in the material is expanding by the same amount. Here is a table of some coefficients of linear expansion. They are very small numbers, as materials do not change much with temperature, and so they are often given in parts per million, Kelvin, so 10 to the -6, Kelvin to the -1. Metals usually have a higher coefficient of thermal expansion than ceramics, such as glass or diamond, and plastics generally have higher coefficients of thermal expansion. It's related to the elasticity of the interatomic intermolecular bonds. Linear expansion is used to calculate the thermal expansion of long, thin bars or beams. It's important in systems such as railway lines or beams that support a building. Now let's do a worked example. The question is, a 1 meter steel ruler is used in a physics lab. The coefficient of linear expansion for steel is 17.3 by 10 to the -6 per Kelvin. How much will the length change over a day of experiments where the temperature in the lab changes from 15 to 25 degrees Celsius? So using our relation for linear expansion, delta L equals alpha L naught delta T, we can start to put in some numbers. Our coefficient of linear expansion in this case equals 17.3 by 10 to the -6. Our initial length is 1 meter, and our change in temperature is 25 minus 15, 10 degrees Celsius. If we calculate this out, we can see that we have a change in length of 173 microns. This equals approximately 0.2 of a millimeter, so we're probably not going to see a big effect on our experiments. We now consider the expansions of gases and liquids. This is similar to the linear expansion we considered previously, except we are now talking about volume instead of length. So consider the change in volume, delta V. This is also proportional to the change in temperature, delta T, and to the initial volume of the material, V naught. We can add the coefficient of volume expansion, beta, and as an equation we now have delta V equals beta V naught delta T, where delta V equals the change in volume, beta equals the coefficient of volume expansion, V naught equals the original volume, delta T the change of temperature. Here is a table showing some coefficient of volume expansion. The coefficients of volume expansion, beta, is often about 3 times that of alpha because the expansion is in 3 directions at once. Volumetric expansion is usually used for gases and liquids. Some final comments on thermal expansion. The expressions for thermal expansion are only approximate expressions that have been observed to be a reasonable fit to experimental data. Many materials have a useful working range in which these equations work well, but some materials do not. Water at low temperatures is a great example of material that does not follow this rule.